Hi everybody and welcome to a new exciting video in the Generating Sound with Neural Networks series. Last time we started building our Autoencoder class and specifically we focused on the encoder component. Today we're going to continue working on the Autoencoder class. Specifically we'll be building the decoder part. In other words, we're going to get like the latent space as the input to the decoder architecture. Then we're going to apply a bunch of like convolutional transpose layers so that at the output of the decoder we're going to get a shape of the data that's like the same that we use as input to the whole autoencoder. Okay, so let's get started with this. So the first thing that I want to do really here is just like to uncomment like this self._build decoder in here. So here, if you guys remember, this _build method is the one that's responsible to construct the whole autoencoder in the constructor of the autoencoder class. But given like we only had like the possibility of building the encoder like in the previous video, so I just like commented out like the self._build decoder and _build autoencoder. But now we are basically building like the decoder so we can uncomment this. Okay, which basically means that we now have to build or implement this _build decoder method. So let's do that. So we'll do a def build decoder. Okay, so now how are we supposed to build this decoder? Well, we can use more or less like the build encoder method as a blueprint, and indeed we'll be starting with a decoder input. Well, sorry about that, decoder underscore input, and here we're going to create a new method called add decoder input, and obviously we're going to be implementing like this method and all the other like methods that we'll put like in build decoder as placeholders in a while. So once we have the decoder input, the next thing is we want to add a dense layer. So we'll have like a dense layer here, and we'll do a self.add dense layer, and obviously we'll need to pass this input layer in here, and we'll be using once again the Keras functional API for adding nodes or layers to the graph of layers. Okay, so we'll continue by doing a reshape layer. And so what we want to do is basically like move from a dense layer into and reshape that into kind of like three-dimensional array. And so we can do that by using this add reshape layer method, and we'll pass in the dense layer. And now we're at the moment where we want to apply all the convolutional transpose layers. So here we'll do conv transpose layers, and we can just do a self._add conv transpose layers, and we'll pass in the reshape layer. Perfect. Okay. So the next step now is the final one, and in other words, we're going to get like the output. So we're going to get the decoder output. So we'll do a decoder output, and this is going to be equal to self.add decoder output. Okay, and here we want to pass this convolutional transpose layers in here. Okay, so now we are ready to create the decoder model, and for that we'll do a model. We'll call like model. We'll pass in the decoder input and the decoder output, and we'll give a name to this model, which is going to be, not surprisingly, decoder. Great. So now build decoder is ready, but obviously we have a bunch of methods that are only placeholders. We need to implement them. So let's start with the first one. So add decoder input. So let's define this. We'll do a define add decoder input. And this is as simple as instantiating an input layer. So we'll do a return input. And here, if you guys remember also like from the input layer of the encoder, we need to specify a keyword argument called shape, the shape of the input. And this is going to be equal to the latent space dimension. So the number of dimensions that we have in the latent space, okay? And here, let me specify the name of this input layer, and I'm gonna put decoder input, as simple as that. Okay, so this is done. Now on to the next one. So we want to add the dense layer. Okay, so let's define underscore add dense layer. And here we'll pass as an argument the decoder input. Okay, so now let's create this dense layer. So we'll do a dense layer over here. And this is going to be equal to a Keras dense layer. And here what we need to specify as the first argument is the number of neurons that we want. Okay, so let's say num neurons, and then we'll just like provide a name, and we'll say decoder dense, as simple as that. Okay, but we haven't defined the number of neurons that we want in this dense layer yet. Okay, so let's do it here. So we'll instantiate this num neurons variable. Now, the basic idea here is that we want the same number of neurons as those that we had before the latent or the bottleneck in the encoder when we flattened like all the data that came out from the convolutional layers. Okay, so how can we get to that number? Well, that's why in the previous video we actually saved like this information here. So the shape before the bottleneck. You may remind this, right? And so what we should do here is basically do a self.shape before bottleneck, but this is not really what we need in this case, because like this shape is going to be like a three-dimensional thing. So it's going to be a three-dimensional array. So it could be like something like, say, 4 by 4 by 32, for example, right? But here we want for this like to be flattened. So in other words, like we want only like a single number here. So how do we do that? Well, we need basically like to multiply all of this items like in this array. So we want, for example, 4 by 4 by 32. Now, I'm not going to be able to do that like only with my mind, so I'm going to like make this like easier for me. So say like we have like this array. So 1, 2, 4. So 1 times 2 times 4, which is going to be like equal to 8. Now we have like a very nice like method that comes with a NumPy that's called prod, which we can use there for doing this. So let me just like import a NumPy as MP, and now when I get down here I can do a NumPy.prod, which stands for product obviously, and here I'm going to pass in the shape before bottleneck so that all the items in the array get multiplied, right? And we get only a number as the output. Right, and so this is like the number of neurons that we want, and we're going to pass it into like this dense layer that we want to instantiate. Okay, and here we can just like return the dense layer, as simple as that. Okay, so now we also have like this add dense layer, but we still have like a mistake, and this is like so simple like to do when you're dealing like with the Keras functional API. And the thing is like, right, so here I've instantiated the dense layer, but I haven't applied it yet to a graph of layers. And for doing that, obviously I'll have like to create like this parenthesis and then pass in the decoder input. And in this way, I'm gonna apply the dense layer to the decoder input. Okay, so now we are actually done with add a dense layer. So now on to like the next step. So we want to add a reshape layer. Okay, so let's define this. So, and here we'll pass in a dense layer like this as an argument. Okay, so what do we want to do here? Well, now, as I said, like from the dense layer, we have basically like a structure that's completely flat. And so what we want to do is just like go back like to a three-dimensional array that has like the same dimensionality in the encoder of the data in the encoder before we flattened like the data after the convolutional layers. Okay. So this is like quite easy like to achieve, because once again Keras comes like with a very nice layer called reshape that we can use. So what we want to do here is say like a reshape layer, and this is going to be equal to reshape, and what we want to pass into a reshape is the target shape, and the target shape is just given by like this shape before bottleneck. Okay, and this is like a three-dimensional array, and here we want to apply like the reshape with this given shape before bottleneck to the dense layer like this. And now we can just like return the reshape layer, or like actually like we can just like make this more straightforward like this. We'll just like return that. Now that we are done with add reshape layer, it's time to add all the convolutional transpose layers. And for doing that, we need to implement this method here, _add com transpose layers. So we'll do that down here. So I'll do a define _add com transpose layers, and as an argument, I'll pass a generic graph of layers called X. And so what we really want to do here is add convolutional transpose blocks. And if you guys remember what a convolutional block is, it's basically just a block of a bunch of different layers. So one is a convolutional layer. In our case, it's going to be a convolutional transpose layer. Then we apply a nonlinearity, and we are going to be applying a ReLU. And finally, we'll apply batch normalization to this. Okay, but in this case, what we want to do is loop through all the conv layers in reverse order and stop at the first layer. Okay, so why do we want to do this? Well, the reason is that we want to obtain convolutional transpose layers that mirror the convolutional layers that we used in the encoder architecture. And so for doing that, we're going to be using basically like the same variables like that we used for the encoder, but we're going to just like go like the other way around. So in reverse order, we start like from the last one, and then we'll go back like to the previous one until we reach the first one. But when we reach the first one, we just stop, because in that case, we don't want to apply like a whole convolutional transpose block, but it's gonna be like a special case, and you'll see how we're gonna treat that. And that specific case is going to be like what's going to make like the output layer for the decoder and for the whole autoencoder. Let's implement this, and we can do it with a for loop. So we'll do a for layer index in a range, and then we'll pass in self dot number of convolutional layers. Now, obviously, like this is not what we want. But let me explain like what we want with a simple example and then obtain that like in code. Okay, so in this case, say we have like 3 convolutional layers. So we would have like something like this. So 0, 1, and 2. So 0 index 1 and 2. Okay, so what we want is the reverse of this. So in other words, we want 2, 1, and 0. And but beyond that, we want to actually like get rid of like the first index right here, right? So we want to just like drop this, and so that we can drop it like down here, so we can ignore like the first convolutional layer. So how can we obtain that? Well, with range, we can add a 1, so that will start basically from the second index, and then we can just like take the reversed of this range here. Okay, and so what we'll obtain is just like something like this. We'll potentially like we would start like with 3 convolutional layers, but then we would like only focus like on the second and third, and then reverse that. Okay, so I hope like this was clear. But now what we need to do is do a x, which is equal to self dot add conv transpose, not layers, but layer. So we're going to just be adding a single convolutional transpose layer. Obviously, like what we want to pass in here is x. So it's the graph of layers. And as an output, we're going to get like the updated graph of layers with the new convolutional transpose layer. Okay, so, and if you guys like remember, this is like very similar to the method that we use for adding the normal convolutional layers like in the encoder. Okay, and so once we've gone through like all of these convolutional layers like in reverse, and we added them, and we stop at the penultimate one, then we can just like return x like this. Okay. So now let me try to implement this add conv transpose layer. And here's where the magic happens. Once again, we need to pass as an argument a generic graph of layers. And here, what we'll need obviously is a convolutional transpose layer, and we can easily add it here. From Tensorflow Keras.layers, we'll add also the com to the transpose. Okay, so let's go back here. So here we'll do a com transpose layer, and we'll instantiate this like this. And here, what we need to do is a filters, and the filters is going to be equal to self.conv filters, and we need to index this. And obviously we need to index this like with this layer index, and here's like an error like that we have in our code like already. So obviously like this add conv transpose layer is going to accept both the graph of layers as well as the layer index, and so I have to add that. So now let me just like take a look at this. So yeah, as you can see here, we have like the same kind of like structure here, because we have like add conv layer, and we pass in the layer index as well as the graph of layers. So let's do like something similar here. So we'll pass the layer index and the graph of layers. And so here, as an argument, we add conv transpose layer receives the layer index as well as the graph of layers. Okay, so now we have the layer index, and then we can pass it down here in the filters. Okay, so we should do like the same thing also with the kernel size, and we'll do a self.conv kernels, and we'll pass in the layer index, and we should do also the same thing with strides, and so we'll do a self dot conv strides, and that's equal to layer index. Okay, so we'll set the padding to same, and here we also want to add a name. And oops, let's do like this, an f string. So we'll do decoder conv transpose layer, and here we'll add like the num layer. So let's say layer number like this. I prefer it layer number. Okay, so but this layer number isn't really like the layer index, because this layer index is going kind of like downwards, right? So we start, say, like from layer index like 4, then we go to 3, then to 2, to 1. But for like the layer number here, we just like want to go like the other way around, because we don't want to start with decoder conv transpose layer 4 and then 3 and then 2. No, we want like the other way around. So how can we obtain that? Well, this is like easily obtainable, and I can create a variable here called layer num, obviously, and we can obtain that by doing a self.numConv layer. So we get the total like number of convolutional layers that we have, and to that we subtract the layer index. Okay, and this will give us like a layer number that's going to increase and basically like start from 1 and go up. Okay. Good. So now we have the convolutional transpose layer, and what we want to do is we want to create like a graph of layers and add this conv transpose layers. So how do we do that? Well, we do like the usual thing that we do with the Keras functional API. So x, the updated graph of layers, is equal to the conv transpose layer, which we apply to the graph of layers like that we receive as an input here. Okay, so now the next step is that of applying a nonlinearity. Specifically, we'll be applying a ReLU as we did for the encoder. And here we can specify like the name. And so here we're going to have like the decoder ReLU. And here this needs to be an f string, and we'll pass in the layer number like this. And obviously once we instantiate a new layer, we need to apply that to the graph of layers, and it's always like the same old blues, right? So we need to apply that like to x, the updated graph of layers, with the newly added convolutional transpose layer. Okay, and finally we want to add a batch normalization layer. So we'll do batch normalization like this. We'll add a name, and the name is going to be equal to decoder bn batch normalization. And here, once again, we need an f string, and we'll pass in the layer number. Now that we have batch normalization, we need to apply it to the graph of layers, and we'll do it like this. And now that we have our convolutional transpose block ready, we can and add it to the graph of layers, we can return the whole graph of layers like this. Okay, so now we should have a way of like adding convolutional transpose layers, and we can go back like to build decoder, and there's only one thing that remains to be done, and it's that of adding the decoder output. Let's build this method. So we go down here, and I'm just going to add, I'm going to add define underscore add decoder output, and as an argument, we'll provide x, which is the generic graph of layers. Okay, so what do we want to do here? Well, we want to create a final convolutional transpose layer, but then we don't want to add like a ReLU activation and batch normalization, but rather a simple like activation layer with like a sigmoid activation function. Okay, so how do we do that? Well, first of all, let's build the convolutional transpose layer. So conv transpose layer. And for doing this, we can basically use like what we've like already like written here. But we should just like readjust this. So now the number of filters, this is like an important one. So we want for like the data that comes out like from this final convolutional transpose layer to be basically like three-dimensional. So we'll have like some height and width, say for example, I don't know, like say 24 by 24, and then have like the channel layer that's equal to 1, and that's because like that will basically coincide with the input shape, so which in the case of the number of channels is equal to 1, and that's because we're dealing with grayscale images or spectrograms, which by the way we can interpret as grayscale images. So if we want 1 here for the number of channels, we want to set the number of filters equal to 1 in this convolutional transpose layer. Okay, then what about the kernel size and the strides? Well, here for this, we can just like take the 0 index that we have in our com-kernels attribute and the 0 index of the list called like com-strides. In other words, like we are getting like the first convolutional, so like all the data that we pass for the first convolutional layer in terms of kernels and strides, but not in terms of filters, because that we must set to 1 if we want to have just like 1 channel like as an output. Okay, so padding remains the same, and the name we need to change because this is not decoder com transpose layer, but we could, well, no, actually like we can leave it like this, but we don't have like a layer number here, but rather like we'll put this equal to self dot num-conv layers, right? So this is like the total number of convolutional layers, and that's if we have like 3 convolutional transpose layers, like in this case, well, here we're going to have like equal to 3, which makes sense because like this is like the highest decoder conv transpose layer that we have in our decoder. Okay, so now we have the conv transpose layer. So what should we do with that? Well, we should apply this to the incoming graph of layers. So in other words, we want to add this node to the graph of layers X. So how do we do that? Well, usual thing that we do with the Keras API. So we'll just apply this to X and we'll get back like this updated graph of layers. And now the final thing that we want to do here is to add an output layer. And this output layer, it's basically just like an activation layer where we use sigmoid. Okay, so what we need to do here is add one final layer from Tensorflow.keras, and that's called activation. Okay, let's go back down here. So this is activation, and here what we want to specify is the type of activation function that we want to use. And as I said, we are going to be using sigmoid. Okay, and now let's add the name of this layer, and we could call it either like output layer or sigmoid layer, like this. Okay, so now we have our new node. The final thing that remains to be done is to apply this, or in other words, add this node to the a graph of layers X. And so we'll do this like this, and finally we can return the output layer like this. Okay, good. So now we also have like this final method here, add decoder output. So now let's just go back to this initial kind of like higher level method called _build decoder and go through it like once again. So how does this work? Well, we first of all create a decoder input, deferring the actual creation of the decoder input to this method _add decoder input. Then we input the decoder input layer in the underscore add dense layer, and we get back like a dense layer. Then that dense layer we input to add reshape layer, and we get back a reshaped layer. And then we add all the convolutional transpose layers that mirror the original convolutional layers that we used in the encoder. And once we get back that, we pass that into the add decoder output method. And in the end, we get like the decoder output. And here we can define the decoder using like this convention. So we instantiate a Keras model, we pass the input, decoder input, we pass the decoder output, and here we just like give a name to the decoder, which is decoder. Okay, cool. Okay, so now we should have basically like most of the things already like in place. The only thing that I want to change here is the summary, which if you may remember from the previous video is like the only thing that really we can call to see what we built with like Keras and Tensorflow. So here, like in this like summary method, public method, we only print the summary of the encoder. Now, I want to do like the same thing, but this time with the decoder. And I can do that again because the decoder is a Keras model. Okay, so now we are ready to run the scripts down here. And I'm just going to leave like this completely unchanged. So you'll see that I instantiate an autoencoder object with these parameters here that we used last time. And then I'm just going to call like the summary method. So let's see if this works. Okay, we're running this, so we're loading Tensorflow and Keras, and here we go. It seems like to work. Like so, here as the first thing we have like the encoder, and we reviewed this like last time, so I'm not going to go through that once again. And down here we have the decoder with all of the different layers and the layer types, and then here we have like the output shape of each layer and the number of parameters here. So now let's quickly review this. So as the decoder input, which is an input layer, we start with like a dimension of 2, which makes sense because that's like the dimension of the bottleneck or the output of the encoder. Then we have like the dense layer, and here basically we are going back to this like dimension here, or this number of neurons, so 3136. And if you guys like remember, this is like the same value that we had here in the encoder towards the end of the encoder when we flattened the data that came out like from the last convolutional layer. And obviously that's not the case because we are mirroring all the structure that we had with the encoder with the decoder. Okay, so then after that we reshape this this layer here, and we move like to a 3-dimensional array, which is 7 by 7 by 64. And again, if we go up here, you'll see that this is like the dimension that we had in the final convolutional, as an output of the final like convolutional block. Okay, which it checks out. That's like what we wanted. Okay, so once we arrive like at this point, then we'll have like the first like convolutional block, which convolutional transpose layer, ReLU, and batch normalization. Then we have like a second one here, second convolutional transpose layer. We have a third one down here, and we have a fourth one here, where if you guys like remember, we only had like one filter here, and we would expect to have like one here because we only had one filter, and so just one channel. Okay, so this is like the output like of the fourth convolutional transpose layer, and then we apply like a sigmoid layer. So all in all, what we have here is like this shape, so 28 by 28 by 1, which luckily is the same as we had as an input to the encoder, or as the autoencoder like as a big whole module encapsulating both the encoder and the decoder. Okay, so down here we have like all the total parameters, and that are divided into like trainable parameters, which are by far the majority, and non-trainable parameters. Okay, so here you have it, the way like you can use like to build a decoder. Okay, so now we are kind of approaching the end of this, the implementation of this autoencoder class. So what remains to be done really is to define like this final like method here in _build, which is _build autoencoder. And that's going to be the topic of the next video in the series. Good. So I hope like you found this video useful. If that's the case, please like leave a like, and if you want to watch like more videos like this and you're not a Sound of AI subscriber, please consider subscribing. If you have any questions, as always, feel free to ask them in the comment section below, or join the Sound of AI Slack workspace, where like you're gonna have a lot of like people who are interested in AI music, digital signal processing, and AI audio more in general, and you can ask questions there and get like feedback from more experienced people, or just like share ideas. Okay, that's all for today. Once again, I hope like you enjoyed this, and I'll see you next time. Cheers.